Hi there, Miss Barber here. The title of this lesson is The Power of Compounding. The learning objectives for this lesson are 1. Evaluate expressions involving powers and roots. 2. Evaluate expressions using the 4 basic rules of algebra. 3. Calculate simple and compound interest. 4. Find annual percentage yield, denoted as APY. 5. Compute present value. And 6. Compare yields and determine time periods. Let's do a brief review of powers and roots. So, basics of powers. A number raised to the nth power is that number multiplied by itself n times, and is called the exponent. So here are some examples. 3 to the power of 1 equals just 3. 3 squared is equal to 3 times 3, or 9. 3 to the 4th means 3 times 3 times 3 times 3, which is 81, and D, 3 to the 0 equals 1. In fact, any non-zero number raised to 0 is defined to be 1. Continuing, let's look at the basics of powers. Negative powers are reciprocals of the corresponding positive powers. Make note, a negative power never changes the sign of any number. Examples. A. 3 to the minus 1 means 1 over 3. It is the reciprocal of 3. So let's continue that with B. 3 to the power of negative 4 means 1 over 3 to the 4, which would be 1 over the quantity 3 times 3 times 3 times 3, which is 1 over 81. Let's continue with our review of powers and roots. So we have some power rules. A to the n times a to the m basically just means a to the, and you add the powers of the exponents together. For example, 5 squared times 5 to the 4th means 5 to the power of 2 plus 4, which is 5 to the power of 6. And if you multiply 5 to itself 6 times, the product is 15,625. Next rule, which is the quotient rule with the same base. A to the power of n divided by a to the power of m is equal to a to the power of the difference of the top power, which was n, minus the bottom power, which is n. So let's look at an example. 3 to the 6th divided by 3 squared is equal to 3 to the power of the difference 6 minus 2, which is equal to 3 to the power of 4, and that is 81. And one more, and that is when we raise an exponent already raised to a power to another power. In that instance, we say that a to the n quantity raised to the power of m is equal to a to the power of the product of n times m. Let's look at an example. 10 squared to the power of 3 is equal to 10 to the power of the product of 2 times 3, which is equal to 10 to the power of 2 times 3 is 6, and that's equal to 1 million. Continuing with a brief review of powers and roots, we will now consider the basics of roots and roots as fractional powers. Finding a root is the reverse of finding the power of a number. Examples. A. The square root of 25. The square root of 25 is equal to 25 to the power of 1/2. We write the nth root as 1 over whatever that root is. Square root is 2. This is equal to 25 is actually 5 squared, so 5 squared to the power of 1/2. This is equal to 5 to the power of the product of the two powers, so 2 times 1/2, which is equal to 5 to the power of 2 times 1/2 is just 1, and 5 to the 1 is equal to 5. Part B, the 6th root of 1 million. That is equal to 1 million to the power of 1/6. Remember, the sixth root is equivalent to writing as to the power of 1 over 6. And that is equal to 1 million is actually 10 to the power of 6th. So 10 to the 6th quantity raised to the power of 1 over 6. And that is equal to 10 to the power of the product of the exponents of 6 times 1 over 6. And that is equal to 10 to the power of 6 times 1/6 is equal to 1. And that is 10 to the 1 is equal to 10. Let's continue with some more review. The 4 basic rules of algebra. The following rules can always be used. 1. If x equals y, then y equals x. 2. You can add or subtract the same quantity to both sides of an equation and still maintain the equality. 3. You can multiply or divide both sides of an equation by the same non-zero number and still maintain the equality. And finally, 4. You can raise both sides of an equation to the same power or take the root of both sides by the same root and still maintain the equality. Continuing with more brief review of 4 basic rules of algebra. Examples. Solve for the indicated variable. Example 1. Solve for w for the equation 5w minus 5 equals 3w minus 25. The goal is to get all terms that contain a variable to one side of the equation and all terms that don't to the opposite side of the equation. I'll begin by subtracting 3w from both sides. 5w minus 3w is 2w. Then we have minus 5 equals 25 remaining. Now let's add 5 to both sides of the equation. So we'll have 2w equals 25 plus 5 is 30. And we have one more item left to do, and that is to get the w by itself. So we will multiply by 1/2 on both sides, and we get w is equal to half of 30. So the equation solves to w equals 15. Part 2. Solve for p for the equation p raised to the power of 1/3 equals 4. Now this is a root power problem. We want p by itself. So to isolate the p, we will raise both sides of the equation to the power of 3. P to the 1/3 times 3. 1/3 times 3 is just 1. So we have p by itself. And the answer is 4/3. 4 times 4 is 16. 16 times 4 is 64. Let's continue. Part 3. Solve for v for the equation v cubed plus 4 equals 68. Begin by getting v cubed isolated, so we will subtract 4 from both sides, and that gives v cubed equals 68 minus 4, which is 64. Now, we need to get the v by itself, and so if it's raised to the power of 3, we'll take the root 1/3 on both sides. So we've got v cubed to the power of 1/3 and 64 raised to the power of 1/3. On the left-hand side, 3 times 1/3 is 1. V to the 1 is just v. And now we're solving for what number must you multiply 3 times in order to get 64. And that turns out to be, we'll go ahead and write 64 as 4 cubed to the 1/3. And that equals 4. So we conclude that v equals 4. Definitions. The principal in financial formulas is the balance upon which interest is paid. Simple interest is interest paid only on the original principal and not on any interest added at later dates. Compound interest is interest paid both on the original principal and on all interest that has been added to the original investment. Example with savings bonds. While banks almost always pay compound interest, bonds usually pay simple interest. Suppose you invest $1,000 in a savings bond that pays simple interest of 10% per year. How much total interest will you receive in 2 years? If the bond paid compound interest, would you receive more or less in total interest? Explain. Let's begin this problem by looking at simple interest. Simple interest first year would be 10% on the $1,000 investment, which is $100. Simple interest on the second year is still 10% on your initial investment, which was $1,000, so that is also $100. The total simple interest for 2 years is the sum of the interest earned in the first and in the second year, which would be $100 plus $100, which is $200. Now let's continue by looking at how compound interest works. Compound interest during the first year is the same as the simple interest during the first year. That is 10% times $1,000, which would be $100. However, the principal for the second year is now $1,000 plus the $100 interest you earned the first year, which would make the principal $1,100. So, compound interest for the second year interest payment will be 10% of, that would be times $1,100. Now you are earning interest on the interest you earned the previous year. That product is $110. So the total compound interest for 2 years is the sum of the first year interest, which was $100, plus the sum of the interest earned during the second year, which was $110, for a sum total of $210. Compound interest increases the account balance faster than simple interest. We have a formula that lets us compute compound interest for interest paid once a year without having to compute the interest each year. This is called the compound interest formula for interest paid once per year. It is A equals P times the quantity 1 plus APR all raised to the power of Y. A stands for accumulated balance after Y years. P is for the starting principal. APR is the annual percentage rate expressed as a decimal, and Y equals the number of years. Example, simple and compound interest. You invest $100 into 2 separate accounts that each pay an interest rate of 10% per year. One account pays simple interest and the other pays compound interest. Make a table to show the growth of each over a period of 5 years. Use the compound interest formula to verify the result in the table for the compound interest case. Let's look at the table first at the simple interest account. In the first year, because it's $100, you earn 10%, which is $10. Let's observe that for years 2, 3, 4, and 5, you still earn just $10. So it accumulates from, in the first year, $110 to the second year, which is $120, third year, $130, fourth year, $140, and finally the fifth year, you have $150. Now let's look at the table for compound interest. In the first year, 10% of $100 is 10. Just like simple interest, however, the new balance becomes the $100 plus the $10 interest you earned, which would be $110. So the second year, you will earn interest of 10% on not the $100 you initially invested, but on the accumulated $110. So your interest for the second year is $11, and your new account balance then is $110 plus 11, and so for the third year your starting balance will be $121. We continue this all the way to the fifth year when your starting balance is now $146.41. You earn 10% on that. So the interest earned for that year is $14.64. Add that to the starting balance and your final balance is $161.05. Let's observe that the compound interest account earns $11.05 more than the simple interest account. Let's now use the annual compound interest formula, which is A equals P times the quantity 1 plus APR to the power of Y. I'd like to identify the parts, so the variables we have are A, and this is what we're looking for. That's what we're seeking. P is your starting principal, often called the present value or your initial investment, and that's $100. The APR is your annual percentage rate, 10% written in decimal form is 0.10, and Y is the number of years for which you make the investment, and that would be 5. Let's summarize. When you solve financial problems, your job is to first identify the formula. Second, identify all the component values of the formula. The next thing to do is to put that formula together. So you'll have A is equal to, and in the place of P, put in the actual value, which was 100, times 1 plus, and for APR, put in the given value, which is 10%, and Y is the power to which it is raised. It's the number of years, so that's 5. Now you begin the solving process, and one of the most important features to remember is the order of operations. You always begin inside the parentheses, so when you solve, we would write A equals 100 times 1.1 to the power of 5. Now we'll use the calculator to compute the rest of the values. I am using a TI-84 plus CE to compute the power. We want the power, so we'll do 1.10, and then we need to raise it, so we use the carrot top looking symbol, to the power of 5 and enter. The output is 1.61051. Let's copy that onto our work. Transferring the value we just computed using the calculator, we will have A, the account balance, is equal to 100 times, and the output we got on the calculator was 1.61051. Never round or truncate during computation, as it can have significant effect on your final outcome. Now let's multiply 100 to the 1.61051. All we need to do here is move the decimal point to the right 2 spaces, and the result looks like 161.05. When we get to the money part, it is okay to round to the cent, and we'll notice that our output of $161.05 matches to the tabular output we computed earlier. Compound interest. Show how quarterly compounding affects a $1,000 investment at 12% per year. Solution. 12% compounded quarterly means 12% divided by 4 and earning 3% every quarter. let's be real cautious here. 12% compounded quarterly does not mean 12% every quarter. So let's begin by doing the first quarter. At the beginning of the first quarter, your principal is $1,000 and you get 3% interest on that. So the interest earned is $30 and your new balance is $1,000 plus 30, which is $1,030. At the beginning of the second quarter, you will earn 3% interest on $1,030. And that amount earned is $30.90. And so your new balance is $1,030 plus $30.90, which results in $1,060.90. And $1,060.90 is the principal on which you will earn the interest of 3% during the third quarter. So interest earned at 3% on $1,060.90 is $31.83. So the new balance at the end of the third quarter is $1,060.90 plus $31.83, which is $1,092.73. That is the principal on which you will earn 3% interest on the fourth quarter. The product of 3% and the principal of $1,092.73 is $32.78. So your balance at the end of the first year will be $1,092.73 plus the interest earned during the fourth quarter, which was $32.78, for a total of $1,125.50. Instead of having to compute the interest earned for each compounding interval, we have a formula that lets us do all of that in one step. That formula is called the compound interest formula for interest paid n times per year. It is written symbolically as A equals P times the quantity 1 plus APR over n, all raised to the power of n times y. A is the accumulated balance after y years. A is often called the future value. P is the starting principal, and P is often called the present value. APR is your annual percentage rate expressed in decimal form. N is the number of compoundings per year. So, for example, compounded quarterly, N would be 4. Compounded monthly, N is 12. And Y is the number of years. Let's get some practice in using the compound interest formula for different compoundings. Example, you invest $1,000 at 10% interest. Find the account balance after 5 years at different compounding intervals. Solution. When solving finance problems, the very first task you must do is identify the formula. And we identify the formula as the compound interest formula, which is A equals P times the quantity of 1 plus APR over N, all raised to the power of the product of N times Y. Now we must identify the parts. The first variable or component to fill is A, and we are looking for the account balance, so I'll follow that with 3 question marks to indicate that's the value we seek. P, the starting principal, often called present value, is $1,000. The APR is 10%, and in decimal form, that'll be 0.1. Y is the number of years, which is 5, and N will vary depending on the compounding intervals we choose. Now, let's put this together, and we'll do it for semi-annually. That's twice a year, so N equals 2. Let's put the parts into the formula. We would have A equals, and for the P, we use 1,000, and in the parentheses, 1 plus. For APR, we use 0.1 divided by N, the number of compoundings is 2, and that'll be raised to the product of twice per year times 5 years. Now we are ready to solve the problem, and we will begin. Remember to always work from the inside of the parentheses. So the formula with the values filled in is A equals 1,000 times 1 plus 0.1 divided by 2 to the power of 2 times 5. Let's work from within. So A equals 1,000 times 1 plus, and the quotient of 10% divided by 2 has an implied parentheses. We perform that, and the result is 5% or 0.05. That is raised to the product of 2 times 5, which is 10. Now let's continue. A equals 1,000 times 1 plus 0.5 is 1.05, still raised to the power of 10. Now, after we do parentheses, the next order of operations is exponents, and we will write A equals 1,000 times, and in your calculator, key in 1.05 to the power of 10 and write out the full expanse of the digits you see on your calculator screen. That will be something like 1.628894627. Do not round or truncate during computation. Now multiply the number we just obtained by 1,000. That would mean moving the decimal place over 3 spaces, which will give the account balance of $1,628.90. Now we'll complete the table for the different compoundings. The table presented has 3 columns and 8 rows. The first row identifies each of the columns. The first row of the first column is called compounding frequency, and reading below we have boxes that go with annually, semi-annually, quarterly, monthly, daily, hourly, and minutely. The second column, the first row of it, is titled formula, and this is where we will complete the compound interest formula for the remaining blanks of the different compounding periods. And the third column with the heading of ending amount gives the actual accumulated account balance for those different compoundings. Let's begin with the first one, annually. Annually means n equals 1. Let's practice filling the compound interest formula. This would be A equals 1,000 times 1 plus 0.1 divided by the number of compoundings is just 1, so 1 raised to the power of 1 times 5. When computed, the result is $1,610.50. Now, beginning in the next one, which is called semi-annually. Semi-annually means the number of compoundings, n equals 2. Let's practice writing the compound interest formula again. So we'll have that the account balance is equal to 1,000 times 1 plus, the 10% remains the same, but the n is now 2. And it'll be raised to the product of 2 times 5. Let's observe that the $1,628.90 matches the computation we just solved. The row following semi-annually is quarterly. Quarterly means the number of compoundings n is equal to 4. The formula is already provided for you with the n value of 4. In the formula, the output is $1,638.62. Let's continue to monthly. Monthly means it is compounded each month. We have 12 months in a year, so n equals 12. Let's practice writing the compound interest formula again, but this time with n equals 12. So we get A equals 1,000 times 1 plus the interest of 10% divided by 12 to the power of the product of 12 times 5. And that outcome is $1,645.31. Let's make a few observations here. Going from compounded annually to compounded semi-annually, we saw an increase of over $18. Now, if we go from semi-annually to quarterly, while it is still increasing, it is not increasing the amount by as much. So when we go from 2 to 4 compoundings, the amount increases by a little less than $10. Let's now continue to increase to 12 compoundings per year. And let's observe that this time we go from 1638.62 to 1648.31. That's less than $7. Now if we go to daily, that's 365 days a year. And so when we go from compounding just 12 times a year to 365 times per year, the amount increases by just a little over $3. Now, let's go to the number of compoundings to hourly. That's every hour of the year. So take the number of days, 365, and multiply by the number of hours in each day, and that'll be 8,760 times per year. And let's notice that this time, as we go from 365 to 8,760 compoundings, it increases by about 11 cents. And then let's go to minutely. Minutely means we'll take the number of hours in a year, which is 8,760, and multiply it by the number of minutes in an hour, which would be 60. So minutely, the compounding will be 525,600 times per year. Now, what's kind of interesting is we go from 8,760 times per year to 525,600 times per year, and there is no change in the ending amount from the previous. So it's still $1,648.72. What this suggests is that there is an upper bound, a limiting value on which the amount of money you can earn after a certain number of compoundings. Even so, let's observe that the more compoundings per year translates to higher yields. Example, planning ahead with compound interest. How much should new parents invest now at an APR of 4.5% compounded quarterly to have $80,000 towards their child's college education in 15 years? Solution: identify the formula. The problem states it is looking for a lump sum investment. And so we're going to identify the formula as the compound interest, which is A equals P times the quantity 1 plus APR over N, all raised to the product of N times Y. Next, identify the parts. A is the account balance, which is also the future value, and the amount sought is $80,000. P answers the question of how much needs to be invested now. That is what we seek, the principal or the present value. So I'll follow that with 3 question marks to indicate that is the value we seek. The APR is 4.5% expressed in decimal form, which would be 0.045. Y is the number of years, which is 15, and is the number of compoundings, and quarterly translates to 4. Now let's put this together into the equation. We'll replace the A with 80,000 equals P remains. That's the value we seek. And then in the quantity we have 1 plus, we replace the APR with 0.045, divided by, we replace the N with 4, and that quantity is raised to the product of N, the number of compoundings, 4, times Y, which is 15. Now we solve for p. When we solve an algebraic expression such as this, we always work from the inside out in terms of parentheses. So let's begin. The left-hand side of 80,000 will remain the same. That is equal to p times. We have 1 plus, and the 0.045 divided by 4 is an understood parentheses. Compute that, and we will get 0.01125, and we'll raise that to the power of the product of 4 times 15, which is 60. Let's continue. We will have 80,000 on the left-hand side is equal to p times, add the two terms in the parentheses, and we will have 1.01125 raised to the 60. Let's continue. On the left-hand side, we still have 80,000, and that's equal to p times the number 1.01125 raised to the power of 60. Use your calculator to compute, and that power turns out to be 1.956455179. We do not round or truncate during computation, and then to solve for p, you would take the 80,000 and divide that by 1.956645179. Again, use your calculator to complete this value. The output on the calculator was p equals 40886.30931. So, the answer to the question, how much should new parents invest now, is parents need to invest $40,886.31 now to meet their goals for their child's college education. Definition: the annual percentage yield, that's APY, is also called the effective yield or simply the yield. The APY is the actual percentage by which a balance increases in 1 year. It is equal to the APR if interest is compounded annually. Let me repeat that. The APY is equal to the APR if interest is compounded annually. And it is greater than the APR if interest is compounded more than once per year. So, let's look at APR and compare that to APY. APR stands for annual percentage rate. APY is the annual percentage yield. To compute the annual percentage yield, use the formula. APY is equal to the quantity 1 plus APR over n to the power of n minus 1. APY equals APR if interest is compounded annually. The annual percentage yield, or APY, is greater than APR if interest is compounded more than once per year. Example: find the APY, that's the annual percentage yield, given the APR, the annual percentage rate. Find the annual percentage yield for an APR of 2.25% compounded monthly. Solution: to compute. First step, identify the formula. The problem says find the APY, so we will use the APY formula, which is APY equals the quantity 1 plus APR over n, all raised to the power of n minus 1. Now let's identify the parts or the components of the formula. The APY is what we're seeking, so I follow that with 3 question marks to indicate that's the value we seek. The APR, that's 2.25% written in decimal form, is 0.0225, and N is the number of compoundings, which is 12. Now let's put this together. That is, replace the component variables with the actual values. We leave APY as is, because that's what we're seeking, is equal to 1 plus, and for the APR, we replace it with 0.0225 divided by N, the number of compoundings. We replace N with the number 12, and we raise all of that to the power of N, which is 12, and part of the formula is minus 1. Now we solve. We'll use a calculator to do that. You are looking at the screen of a TI-84 Plus CE. We are going to use this calculator to compute the left-hand side of the problem. Let's begin with, we will mark parenthesis, 1 plus. And then it's important to understand that the 0.0225 divided by 12 in the order of operations is already in the parentheses, in the implied parenthesis. So we will do 0.0225 and divide that by 12, close the parenthesis. Then we need to raise this to the power of the number of compoundings, which is 12. Let's move to the move to the right, and we have to still subtract. So use the minus 1 for the part of the formula and press enter. The output we get is 0.0227334876. Let's copy this onto our work page. So when the formula is solved, we get that the APY, that is the annual percentage yield, is equal to 0.0227334876, and we write the APY as 2.27%. Continuous compounding. Let's compare the effect of different compounding periods on the annual percentage yield for an annual percentage rate of 10%. If n is 1, meaning that it is compounded just once per year, it is still 10%. Let's quickly go through this. If that 10% is compounded, say the number of hours in a year, which would be 8,760, the 10% APY for n equals 1 increases to 10.5170287%. The idea or the thought is that most of us would like to think the more compoundings per year, the greater the return, and that is kind of true, but the rate of increase becomes so ineffective it appears to settle in on a value. Let's look at 1,000,000 times per year. That APY is 10.517091260.8%. That is in effect what the APY was for n equals the number of hours in a year. Let's just continue to increase, so we will go to 1,000,000,000 times per year. Let's observe that the APY is still 10.51709, and the digits following that increase by a little bit, which is to 26818%. Again, let's observe that as the number of compoundings increase indefinitely, that the APY settles in on a value. Provided is a graph that illustrates the behavior of continuous compounding. The graph is placed in the first quadrant. The horizontal axis is labeled the compoundings per year. The units are from 0 to 100 and 10-unit intervals. The vertical axis represents the annual percentage yield, and it begins with 10 as the starting annual percentage yield and increases by the units of 1/10 in 1/10 intervals to 10.5. The graph that demonstrates the continuous compounding increase shows a rapid but smooth increase from 0 to about 10-15 compoundings per year, and then while the graph continues to increase, it does so at a much lower rate, and it has the appearance of a horizontal graph as it gets closer and closer to 100. This graphic also includes a horizontal line whose value is at 10.5170926818, and this demonstrates the upper bound, or which is also the value in which the APY settles as the number of compoundings increase. We have a formula for continuous compounding interest. It is A equals P times E to the power of APR times the number of years Y. Again, A is for the accumulated balance after Y years, and it is often called the future value. P is the starting principal. It is often called present value. APR, which is sometimes called the nominal rate, is the annual percentage rate, and we express this in decimal form. Y is the number of years. E is a special irrational number with a value that's approximately 2.7182818. When solving problems involving continuously compounded interest, use the E key on your calculator. Do not attempt to approximate this numerically. Example for continuous compounding interest. You deposit $500 in an account with an APR of 4.25% with continuous compounding. How much will you have after 10 years? Solution. As always, first identify the formula. The problem states continuous compounding, so we will use the continuous compounding formula, which is A equals P times E to the power of APR times Y. Next, identify the parts or components of the formula. A is what we're seeking. We want to know how much we will have after a certain period of time. P, which is principal and more often regarded as present value, is $500. It is the lump sum we will initially deposit. APR is given as 4.25%, and in decimal form it is written 0.0425, and Y is the number of years, which is 10. Next, let's put this together. A is equal to 500 times E raised to the power of the product of 0.0425 times 10. Let's compute this using our calculator. I am using a TI-84 Plus CE calculator. Let's compute this continuously compounded interest account balance. We will begin by keying in 500 times. Now the next thing is we must find the E key, and it is the blue function right above what looks like an ln. So we're going to push second, an ln, and we get E raised to blinking boxes. And in that blinking box we will key in 0.0425 times 0.425 was the interest rate, and that Y is the number of years, so we'll key in 10 and then press enter. The value we get is 764.7952098. Let's transfer this to our working page to complete the problem. Let's transfer the A value we solved using the calculator. So A is equal to $764.80. Stated correctly, we would say the accumulated balance after 10 years is $764.80.